alloys for high temperature applications and aerospace materials. Today has been two sessions, before lunch and after lunch. The before lunch session include two topics of emphasis, one on ultrasonic additive manufacturing and other one on welding response of precipitation strengthened cobalt nickel based superalloys. I welcome you all to the second day of this two-day national seminar. Let me begin to end this seminar. You are ready to hear, but let the session get started. Let me introduce you the first resource person of the second day. After receiving his MTech from IIT Madras, he joined the prestigious Regional Center for Military Airworthiness Materials in Hyderabad in 1998. Later, he joined IIT Madras in 2008 and served till 2020 before he joined IIT Hyderabad. Currently, he is serving as a professor in the Department of Material Science and Metallurgical Engineering at IIT Hyderabad. Over the past 15 years, he has worked on several sponsored research and industrial consultancy projects and taught courses in the fields of materials joining and additive manufacturing. He has authored or co-authored more than 120 research papers in referred journals till date. The department is fortunate to have him here this morning. Ladies and gentlemen, put your hands together to welcome Professor Kabita Vidya, the first resource person of the second day of this seminar of this day. Welcome, sir.
Thank you.
I request the speaker to honor Professor Janakiram Garu with a bunch of flowers.
Thank you.
Professor Janakiram will be addressing us on one of the most emerging manufacturing technology, that is ultrasonic additive manufacturing. All the students are interested to make notes of his lecture. Over to you, sir.
Am I audible? Not really. I feel like something is getting into my mouth. Should be fine. Am I audible to the last one? Yeah, I think I will manage. Good. So that stick is not enough. I need a pointer. That is not enough. How do I manage? So, good morning to all of you. How many of you are from institutes other than MGIT? Other than MGIT, students? Nobody? And I believe most of you are in mechanical engineering and metallurgical engineering. Right? Okay. So how many of you heard of this ultrasonic additive manufacturing? Nobody? Yes. How many of you are familiar with additive manufacturing? Please come up here. See, this ultrasonic additive manufacturing is not a well-known additive technique, but it is actually a very interesting solid-state additive technique, and it is considered a mainstream additive process already. Right? So, to whatever it is worth, today I will only talk about ultrasonic additive manufacturing. There are many other additive approaches, additive processes. Most of them involve fusion, melting and solidification. But today we will look at a process which can help us produce a three-dimensional part without involving melting and solidification. Okay? Now, as I said, metal additive manufacturing can be carried out using multiple approaches, multiple processes. We have several classes of additive manufacturing techniques. Out of them, two are considered direct metal additive techniques, and those two are the well-known powder bed fusion and directed energy deposition techniques. In powder bed fusion, you have an arrangement for spreading a thin layer of powder, then you scan it selectively using a laser or electron beam, and wherever the beam radiates the powder layer, you have heating, melting, and as the resource moves away, the molten metal solidifies, forming a solid track of metal along the line of laser scan or electron beam scan. After generating a layer, you lower the bed platform by one layer, then spread another layer of powder and start scanning for the next layer. So this process is repeated until the entire part is built from bottom to top, layer by layer. Additive manufacturing is essentially a process involving progressive material addition. Progressive material addition, guided by digital data of the part that you want to produce. So any additive manufacturing process involves the same process steps. You make a CAD model, then you tessellate it, then slice it into number of horizontal cross sections and generate material deposition paths. You have a software to do all this. Then these layers are created one over another to produce the part in a additive manner. In conventional manufacturing techniques, especially involving machining, you don't actually add material, you subtract material progressively, of course. But this is entirely opposite. You add material just where you need to produce a three-dimensional shape or component. Now, these techniques, powder bed fusion and directed energy deposition, involve melting and solidification, and you can achieve very complex parts, complex shaped parts, and very often you get 100% density without much of a problem, and you can do a suitable heat treatment to achieve the optimum microstructure and properties. So these are good. But then many engineering methods are susceptible to cracking during welding or during additive processing involving fusion, right? For example, if you consider an aluminum copper alloy or aluminum magnesium silicon alloy, heat-treatable aluminum alloys, they all can undergo cracking very severely during welding or additive manufacturing using these powder bed fusion or directed energy deposition techniques. Similarly, once melting and solidification is involved, there are many other undesirable effects like development of residual stress. You are now uniformly heating and cooling the material, so some residual stress. Differential heating and cooling always leads to some internal stress, right? That is your residual stress, which can cause distortion of the part or some inferior mechanical properties, especially fatigue. So, your choice of build materials is limited with powder bed fusion and directed energy deposition techniques because some engineering alloys, the majority of engineering alloys are susceptible to cracking during fusion process. If you consider a high-end creep-resistant nickel-based superalloy like CF247PC, that is also susceptible to cracking during additive processing or welding. And I can give many other examples in other alloy systems. For example, if you consider a titanium alloy, let us say metastable beta titanium. Here we have a different kind of problem. Cracking is not the issue, but when you additively process, it is unavoidable to have undesirable grain boundary alpha layer, which will lead to precipitate free zones along the grain boundaries, leading to strain localization and inferior mechanical properties. And this grain boundary alpha formation cannot be avoided if you fusion process a metastable beta titanium alloy. Right? So, like this, you have multiple problems or challenges in fusion-based techniques. So, what is the solution? If you can develop a additive process without involving melting and solidification, then all these problems can be taken care of, right? So some of the additive approaches utilize this concept, and you have some solid state additive techniques which can be subdivided again into direct and indirect solid state additive approaches. Let us first discuss about this indirect or two-step. I should not be touching it,
Yes.
but I will be pointing like this. So let us look at these indirect or two-step solid-state additive approaches. Some of you might have heard about binder jetting. In this case, you spread a thin layer of powder, which may be any metal. Then inkjet print a binder onto the powder layer, just where you need. Wherever binder is printed, the powder particles get bonded together, not in a very strong way, but enough to have sufficient handling strength. So you keep spreading the powder layers, keep printing the binder, and produce a part from bottom to top, layer by layer. And this part is now metallic, but the powder particles are only bound by a weak binder, not very strong, right? So essentially, you produce a green part, right? This is like your metal injection molding, where you injection mold a metallic powder along with a plastic binder, get a green part out, then burn out the binder by heating to some temperature, and then continue to heat to the sintering temperature, where solid state sintering will take place, and you have a stronger part, fully dense part. Right? So this is called a two-step solid state approach. Because in the first step you are only producing a green part, and then you are subjecting the part to solid state sintering. There is no melting involved here. And this approach is becoming very popular these days. And of course, there are some limitations, but it is considered one of the scalable metal additive techniques. That means many additive techniques are not suitable for mass production. If you want to produce 1 lakh parts, many additive techniques are not the right techniques. But binder jetting has this special capability. It can be used for mass production. Now, you can also do this in a different way, what is known as fused filament fabrication. In this case, you first load a metal powder and produce a plastic filament. So you produce a thin wire of a plastic which is loaded with metal powder to a certain volume fraction, like 80%, 75%. Then extrude this filament by heating it to something like the glass transition temperature of the plastic, and therefore you have a semi-molten type of state, and that is extruded through a small orifice, and the extruded is deposited the way you want, right? And by successively depositing these extruded layers, you produce a three-dimensional part, right? Once again, as you complete part fabrication, what do you have? You have metal powder bound only by the plastic, right? Again, it is a green part, right? Then same process again. You burn out the binder, go on to sintering, solid state sintering, to produce a fully dense part. Here again, you have two steps. In the first step, you produce a green part, then solid state sinter it to obtain the final compound. Right? So both approaches are now becoming very popular. There are many advantages in utilizing these binder jetting used filament fabrication techniques. If you have an aluminum, zinc, magnesium, copper alloy like 7075, which is impossible to fusion process because it is so susceptible to cracking, that material can be readily additively processed using binder jetting or powder bed fusion, right? So that is the main advantage. Similarly, in fusion-based techniques, during solidification, some elemental segregation is unavoidable. So you have some compositional inhomogeneities. And the segregation can often lead to formation of some undesirable intermetallic phases in the interdisciplinary meetings. But all this happen only when you melt, right? But in binder jetting and fused filament fabrication techniques, you are not melting the material, so no question of any segregation, no question of any undesirable phase formation due to segregation. Then, in powder bed fusion or directed energy deposition, it is very likely to get an undesirable columnar grain structure for reasons beyond your control. You may be able to exercise some control over the certification parameters, thermal gradient and growth rates, and therefore control the growth morphologies, but that is to some extent. You don't have full control over the certification process. So very often you may end up with a columnar grain structure which gives you anisotropic properties. You have a certain property in the build direction, you have a certain degradation in property in other directions. Right? Anisotropy is non-uniform properties with respect to direction. But in parts produced by binder jetting, your properties are fully isotropic because microstructure is uniform everywhere. Right? So you get fully isotropic properties. This is one of the important advantages of binder jetting technique. Right? Similarly, if you want to produce a part in multi-materials or in functionally graded materials, you need to have metallurgical compatibility if you want to use fusion-based techniques. You may be able to produce a smooth gradient in composition if you consider a very simple benign system like copper nickel, right? They have solubility in each other, right? Good solubility, full solubility in each other, right? Copper nickel is an isomorphous system. So you can easily achieve smooth gradation in composition, 100% copper on one side, 100% nickel on the other side. Fine. But what if you want to produce the same thing with nickel titanium? Not possible because nickel and titanium have limited solubility and they can react to form brittle electrometallics. What if you want to produce a steel aluminum multi-material part? Not possible again because you have metallurgical incompatibility leading to brittle intermetallic formation. And once you have these undesirable phases, cracking is unavoidable. Right? But in solid state additive techniques, you can actually have good tolerance. Right? You can put, let us say, titanium and nickel together, aluminum and titanium together, nickel, titanium together. Because you are not melting, they are not actually getting mixed up, right? So this is another advantage, you will see. Now, these two-step approaches, binder jetting and powder fused filament fabrication, are good, but they are involved in two steps. Are there any techniques which can produce a metallic component directly in solids? Yes, there are two interesting approaches. Both are now commercially used. Both are not well known yet, but both are in commercial use. Right? One of them is based on ultrasonic welding of thin foils. That is our topic of interest, ultrasonic additive manufacturing. And the other is based on friction deposition, and it is now referred to as additive friction deposition process or melt, MELD, melt. It is just a fancy word to be combined, to bring two materials together. Right? We will not look at melt today. We will talk about ultrasonic additive. These direct solid state additive approaches have some unique capabilities. Right? You can do things that cannot be done by these fusion-based AMP techniques. And I have briefly mentioned about some of the advantages. We will look at them again later on. Now, this ultrasonic additive manufacturing process was originally developed by a company called Solidica Incorporated. And the inventor is a welding specialist, Dawn White. She was in Edison Welding Institute, and she conceived the idea of using ultrasonic welding of thin metal foils for producing three-dimensional parts. And then she founded a company called Solidica around 2001, 2002 time. And this Solidica company commercially introduced ultrasonic consolidation machines. In those days, it was called ultrasonic consolidation. In 2004, I think, 2004. Right? Now, in ultrasonic additive manufacturing, you have a rotating solar rod, which actually vibrates in natural direction at a certain ultrasonic frequency, like 20 kilohertz, 35 kilohertz, like that, at a certain amplitude. The amplitude of vibration is very small, something like 12 micrometers, 15 micrometers, 20 micrometers, not much. So visibly you cannot see any oscillatory motion. Now this solid rod runs over a thin metal foil. The metal foil has some standard dimensions. It is 25 millimeter in width and 150 micrometer in thickness. So you have a thin metal tape, let us call it tape, because it is like 25 millimeter wide, 150 micrometer thick. Right? You lay a layer of tape, then run your solid rod along the length of the foil. Initially do tap welding, that means only welding at certain points along the length of the tape, and then run the solid rod again to cause complete welding. Right? Now, this ultrasonic welding can be considered as a microscopic friction welding process. All surfaces are covered with a thin oxide layer, no matter what is the thickness. Maybe just 1 or 2 nanometers, but all metal surfaces are covered with a thin oxide layer. Then no surface is perfectly flat. Right? You always have some microscopic roughness. If you consider a metal foil or the base plate, if you consider a base plate and place on top of it an aluminum metal foil. If you look at the interface, it would be something like this, right? You have contact only at some point, and there are some voids, right? And for achieving metallurgical bonding between this base plate and the foil, you have to actually get rid of the oxide layer and promote intimate contact. What is intimate contact? Contact at distances where interatomic forces can come into play. That means they have to be really intimate. And this is achieved by a combination of friction and plastic diffusion. What is done is you apply a certain normal force on the sonotone which is traveling over the foil while it is vibrating in transverse direction. Right? Now, the sonotone grips the foil which is to be welded, and the foil actually keeps vibrating along with, keeps moving along with the sonotone, and you are applying some normal force. That means the foil is now in frictional contact with the base. Right? Now this friction helps remove the surface oxide layers. This friction also generates some heat, and that lowers the yield point or yield strength of the material. So there will be some plastic deformation taking place. As the surfaces undergo plastic deformation, more points come into contact. In other words, these voids become smaller and smaller progressively. And this happens over several cycles. And eventually you have a perfectly flat surface which is in intimate contact. The foil is in intimate contact with the base plate, and the oxide layers have broken off. They got removed because of the friction. That is how you achieve metallurgical bonding of a foil of material onto the base plate. Right? That means you have produced a layer of your part. Then on top of it, place another foil, do ultrasonic welding, you produce another layer. Right? Now, you are only welding foils of standard dimensions, right? 120, 150 millimeter thickness, 25 millimeter wide, right? But how are you shaping? The shaping is actually done in this process by CNC machining, which is integrated with the ultrasonic welder. So in the commercial machine, you have a provision for CNC machining, automatic CNC machining. So this CNC machine will actually carry out the contour machining to generate this shape. Right? It will be clear after I show the video of the process. Now, in the standard process, you have a base plate which is firmly anchored to an anvil, you bolt it to an anvil, which can be resistively heated to something like 200 degrees centigrade. If you want, you can use 100 degree preheat or 150 degree preheat or 200 degree preheat. There is some advantage in using that. Then you deposit these foils side by side to cover the entire layer area. Right? The foil has only 25 millimeter width, but if your part is 100 millimeter wide, you have to place 4 metal foils side by side. Right? Then you can cover the entire layer area. You cover the entire layer area by placing the foils side by side. Weld them to the base. Then on top of it, Place the foils again side by side to cover the entire layer area and weld it to the previously deposited layer. Right? And by keep doing this, after you do this for let us say 15 layers or 20 layers, you call for machining, then the CNC machine will come and shape the deposited material. Then you continue with further part fabrication. Typically, this machining is done after depositing 10 layers or 20 layers, something like that. But it is possible to call for machining after depositing each layer. That is entirely your discretion. Right? Now, during ultrasonic welding, importantly, there is no serious heating of the material. At the rubbing interface, temperatures raised, but that is less than 0.5 homologous temperature of the material. That means in the case of aluminium, at the rubbing interface, temperature is not going to be more than 300. Even that is restricted to a very, very thin region at the interface. Just few micrometers get really heated up. Maybe 20, 30, 40 micrometers next to the rubbing interface. You may have some heating. But if you actually touch the part while it is being built, you feel no real heat. Right? So there is no serious bulk heating of the part. Although there may be some temperature rise at the rubbing interface of the foils, but there is no bulk heating of the part. You can use any metal foil, any metal that can be produced in the form of foil can be used for part fabrication. Mind you, not all metals are ductile enough to be rolled into thin metal foils. Aluminum can be readily produced in the form of foils, copper, many other metals, but not all metals. Now, let us look at this video. How do I play the video? Where is it? You actually go to the separate file and come out of your script. Okay, in the meantime, any questions on whatever we have seen so far? See, heating itself is not very high. The thermal cycle is very benign, right? And heating to something like 200 degrees centigrade or a thickness of, let us say, 25 micrometers for some milliseconds. These even microseconds, in my opinion, doesn't really cause any perceivable change in my system. Right? Yes. So now here the machine is preparing the base. First it is flat machining it. Now it is laying the tapes, right? The tape is laid, it is tack welded first, and then it is fully welded. Right? So now it has covered the entire layer area, and CNC machining is happening to shape, right? Now after that you deposit foils for the next layer, and then do machining. And this machining can be done after depositing, let us say, 1 layer or 5 layers or 10 layers, depending on the geometry of the part and depending on what you want to do. And this process continues, foil deposition and machining continues until the entire part is built. Now, you may ask me, is this a truly additive technique? No, there is also material subtraction involved. So this is not a fully additive technique. In fact, it is a hybrid technique involving both material addition and subtraction. And such hybrid approaches are actually very advantageous. In powder bed fusion or directed energy deposition, which are purely additive processes, you always have some surface toughness. Because in additive manufacturing, this curved surface is approximated by a series of straight-sided layers, right? So you have what is known as stage stepping effect on the surface. So the thicker the layer, the more prominent is the stage stepping effect. Even otherwise, in powder bed fusion or directed energy deposition, very rarely you produce fully satisfactory surface finish for a given application. Right? Now, in ultrasonic additive manufacturing, the surface finish is as good as conventionally machined parts because the part is shaped by machining, right? So there is no stage stepping effect, and surface finish of the component can be as good as your conventionally machined components. That is not the case with pure additive techniques like powder bed fusion or directed energy deposition techniques. After part fabrication, very often you have to do some finish machining of surface finishing operations. Right? Okay, this video is done. Okay, let us go back to the presentation. Next slide, please. Yes. Maybe not sure. Is the next slide? I'm not sure if this is the next slide. Okay, let us see. You may wonder, this solid state ultrasonic welding can really bond the layers strongly. How sure are you? Right? Because there is no melting, there is no significant heating, but are you really achieving strong bonding? Because how strongly the layers bond with each other will eventually determine how strong is your part. Correct? Yes, when properly done, ultrasonic welding can produce an excellent solid state bond without actually no change in microstructure of the base plate or the layer that you are depositing. For example, this is the EBSD micrograph of a nickel part produced by ultrasonic consolidation. And you look at the interface here. This is one layer, this is one layer, this is another layer. And you have actually the interface here. You can make out the interface. It is almost like the grains actually are meeting. They are not, there is no grain continuity across the interface, but they are just meeting each other. There are some little strains in the grains immediately adjacent to the, immediately next to the interface. That is because of the plastic deformation. So you see some smooth color changes in the grain. That is an indication that there are some strains in the grains. But that is fine. no recrystallization, no diffusion, right? No grain continuity, but very good solid state bonding. And this is very much possible therefore, right? When properly done, ultrasonic welding can give you a very strong bond, as strong as what you can achieve with fusion, right? Like welding or fusion based anything. So there is no need to really doubt the capability of this technique in terms of producing strongly bonded layers. Right? Now, I think there is one slide missing. Here there is one slide. Where is it? Okay, fine. Let me come back to that again. Okay. We can actually do one thing. Okay, can you go out of Lego? No.
Your file shall exit from the
Are you sure?
file 6 is it?
And go. I'm not sure why that happened. Something wrong with the copying process. But that is a very important slide. I don't know how to proceed further with this now. Do you agree? Yeah, fine. That slide, the missing slide, actually talks about the effects of process parameters. What are the process parameters here in ultrasonic additive manufacturing? The speed with which you roll your sonotron, right? That is your welding speed. And the normal force that you are applying, and the vibrational amplitude, and the base plate temperature, right? You can actually choose to build a part at room temperature or use a certain preheat like 100, 150, 200. The energy input increases if you increase the normal force and also the oscillating amplitude. If you reduce the speed, your energy input is increased. Am I right? And if you properly optimize the process parameters, you can achieve very good bonding, and the interfaces are actually not quite discernible. You cannot actually distinctly see the layer interfaces if process parameters are well chosen. Right? Now, in ultrasonic additive manufacturing, you have three problems to address actually. These problems are not fully addressed yet. The first problem is what is known as type 2 defects problem. Here I show you a low mag microstructure of an aluminum part produced using ultrasonic additive, and this is in as polished condition. There is no etching. Now, how are you making a layer? By placing the foils side by side to cover the entire layer area, right? Now, during ultrasonic additive or ultrasonic welding, you can always achieve good bonding between the foil that you are trying to weld and the bottom, that is the base. But it is always difficult to achieve good bonding between two adjacently laid foils, right? Because that is where no frictional movement is obtained, right? You don't have any frictional contact there. For example, this is one foil of the layer. This is another foil of the layer. In between there is a gap. This gap is very small. Sometimes it is only 10 micrometer, 5 micrometer like that, but it is still a defect. Right? It is a defect. If your process parameters are not optimally chosen, then you can have some unbounded regions between foils of different layers. Right? So this is one layer, this is another layer, and in this case, process parameters are not well chosen. So you have some unbounded regions here. These black spots are the unbounded regions. Some regions along the foil interface have got properly bounded, but there are some unbounded areas. And these defects are what are known as type 1 defects, shown by the white arrows here. They can be readily overcome. All you need is careful process optimization. If you do that, you can 100% remove the type 1 defects. The missing slide actually shows that. The type 2 defects, which occur between foils within a layer, right, are very difficult to overcome. There is no easy solution to this. Right? I will propose some solutions. I will show some of our work later on. Now, given that you have these defects, type 2 defects, between adjacently laid foils, how do you produce a part? If you keep placing the foils one over another in a monotonous manner, you have this defect running all along the length of the part, right? Therefore, you have to stagger your foil placement. Use a brick style foil placement, for example, as shown here. Right? In other words, this type of defect and this type of defect, this type of defect are not connected because of your foil placement in a brick style approach. And this is adopted in commercial ultrasonic additive manufacturing. Right? But in any ultrasonically additive manufactured part, right now, you have these type 2 defects. Type 1 defects can be readily eliminated. All it needs is careful process optimization. But type 2 defect is difficult to overcome. Now, one of the possible solutions for type 2 defects is using a very wide foil. Right? Why use only 25 millimeter wide foil to cover, let us say, 200 millimeter wide part? Why not use 200 millimeter wide foil, place it, and then keep welding it? Your solid rod can be 25 millimeter in size, in width, but you can successively weld it. And when you do that, there is no type 2 defect within that layer, right? Because you are using a single wide foil to cover the entire layer area. So one layer is only one foil. But what is the disadvantage of this? You can only choose your foil weight for a given part. If you know that your part is 200 millimeter in width, you can say my foil can be 250 millimeter in width or 225 millimeter in width. Right? But once you have a machine with 200 millimeter wide foil, and if you want to produce 50 millimeter wide part tomorrow, what will happen? You have to machine up the extra material. Right? So the amount of material that is getting wasted will be much more. If you use 25 millimeter wide foil and place side by side, the material wastage is minimized. If you use a very wide foil and produce only a small part, then much of your material is getting machined out. Therefore, you are not fully realizing the benefit of additive processing. So this is a possible solution, but it is not implementable industrially. You can always do it for a fixed size part. If you know that you have your part always 200 millimeter wide, then you can use it. You can use, let us say, 225 millimeter or 250 millimeter wide part. But if you want to change the part size, especially if you want to change the part size to a smaller one, then you have serious loss of material, wastage of material. Another approach is, that is a possible approach which we have demonstrated and published, is utilizing, let us say, friction stir processing to heal type 2 defects. In this case, you don't use any brick style foil placement. Keep the foils one over another, keep building the part to a certain height, like 6 millimeter, 10 millimeter. Then run your friction stir tool along the type 2 defect, which actually gets healed. And for this, you don't need to have any additional setup, because in ultrasonic additive itself, you have a CNC machining possibility, right? So instead of using the milling cutter, you use friction stir tool, and that can be readily implemented. And the other solution is to use, let us say, aluminum silicon coated aluminum foil. Aluminum silicon has much lower melting point compared to, let us say, aluminum manganese foil. Now you build a part using this coated metal foil, and after part fabrication, heat it to a temperature where only aluminum silicon can melt. Right? Aluminum manganese or whatever is your base metal foil doesn't melt, but this coating aluminum silicon melts. And this molten aluminum silicon acts like braze metal. So it will actually fill the type 2 gaps or defects. And if one can use these coated aluminum silicon metal foils, one can readily produce a part without any defect, type 1 or type 2, because all these defects will get healed by the brazing action of the molten metal. Right? So this is another possible solution. And these are industrially implemented? No, not yet. These are still in R&D stages. Now, another problem in ultrasonic additive manufacturing is the problem with substrate stiffness. Stiffness is geometry dependent, right? For example, if you want to build a thin lid using ultrasonic additive, you can actually choose to build it in longitudinal orientation, or transverse orientation, or lateral orientation, or let us say 45-degree orientation, with respect to the travel direction of the sonotone. Right? The sonotone is always vibrating in transverse direction. Right? Now, in the longitudinal direction, you have the stiffness problem. As you build the part to a greater height, the part keeps vibrating. Right? And once the part keeps vibrating along with the sonotone, no proper bending can take place. So after building the part to a certain height, there will be problem with layer addition, because the part is no longer stiff enough to receive the ultrasonic energy. The part also keeps vibrating. then there is no relative motion between the foil that you are trying to weld and the base. And once there is no relative motion, no friction, no heating, no upside layer removal, so no proper bonding. Right? Therefore, this orientation cannot be used for building a tall component. You can use this orientation for building it to a greater height, because here geometrically your stiffness is more, right? This orientation gives you better stiffness, substrate stiffness. But what is the problem here? If this is only 25 millimeter in width, you can produce it by depositing one tape, right? Per layer, one tape. But here, per layer, you have to make several tapes side by side. Right? You have to place several tapes side by side. That means this component will have many type of defects as compared to this. Right? So it is a balance between the substrate stiffness and the number of foils that you are laying to cover the layer area. In other words, type to defects. You have to balance between these two considerations to be able to identify the optimum path orientation for ultrasonic additive manufacturing. Generally, in this orientation, the maximum achievable aspect ratio is only 1:1. 1:1. That means if your rib width is 25 millimeter, you can only build it to 25 millimeter height. That's all. Subsequently, you will have problems with bonding of the foil because the substrate also keeps vibrating. Yes. Now, how long I may have? I don't have much to talk about after this. Maybe 10 minutes? Yes. Yeah. Now, I said because there is no significant heating in ultrasonic additive, no melting, no solidification, you can put many dissimilar metals together and produce parts. Right? And we have done actually ultrasonic consolidation using many different material combinations. Let us say aluminum 3003, which is an aluminum manganese alloy, plus let us say copper, titanium. Where is the cursor moving? Oh, this is good. I can always use this cursor. Okay. So I can use copper, titanium, nickel along with aluminium. Or I can use aluminum manganese alloy along with aluminum copper magnesium alloy 2024. Then I can also probably use aluminium manganese along with an alumina composite foil. Produce multi-material parts. All these were done successfully. For example, here you see several copper foils welded to each other. Here you have aluminum, and after building the part to certain height in copper, again you switch to aluminum. And you are looking at that region of the part, right? And here there are several copper layers, but none of them are really deserted. Your bonding is so good. Right? And if you do, let us say, an elemental scan across this aluminum copper interface, you see a very sharp change in composition, suggesting that there is no real diffusion of aluminium into copper or copper into aluminium, which is good. You don't want excessive diffusion, excessive interaction between aluminium and copper. which can lead to formation of undesirable Al2C. Right? So something like this is impossible to achieve with your powder bed fusion or directed energy deposition techniques. This is very beautiful, right? And you have many applications of this in thermal management devices or heat sinks. Now, aluminum manganese is not that strong, but it is quite ductile. Aluminum 2024, which is aluminum copper magnesium, is precipitation hardened and it is very strong. So you can actually make an aluminum part using alternating layers of, let us say, aluminum manganese and aluminum copper magnesium, right, without any problem. You can keep doing it, and you may have one or two defects here, but these were not done under conditions of careful process optimization. You can always get rid of those by careful process optimization. Our type 1 defect is never really a concern. Type 2 defect is the main concern. Now, what about aluminum titanium? Beautiful. You can see an SEM micrograph, aluminum titanium, and you can also change the thickness of aluminum layers or titanium layers the way you want. No diffusion or intermetallic formation at the again, quite good. What about this composite? Alumina tape, along with, let us say, aluminum manganese, produce a multi-material part. One layer composite, another layer metal. Keep doing it until the entire part is there. And at the interface, you see how well the bonding is between the composite foil and your aluminum manganese foil. You can also produce fiber reinforced composites. For example, after laying a layer, you place silicon carbide fibers, right? And then weld foils over. During welding, ultrasonic welding, because of plastic deformation at the interface, the fiber gets fully embedded, no gaps. For example, here you see is silicon carbide fiber fully embedded in aluminum matrix. And these fibers can be as closely spaced as shown here. Right? Still you have no gap in between. That means there is sufficient metal flow to cause complete fiber embeddment. That means you can produce real good silicon carbide continuous fiber reinforced aluminum matrix composite using ultrasonic additive. Such a thing is not possible with any other additive approach. Right? Now, you can also place stainless steel wire mesh, let us say, in between aluminum layers to cause area stiffening. You can stiffen the entire area by placing a stainless steel mesh, and the mesh gets properly embedded again. And interestingly, you may notice that during ultrasonic welding of this coil to this, the crossbeam members of the wire mesh also got ultrasonically bonded. Right? Here it is not supposed to be any bonding. Originally, the fiber in the wire mesh, here there is no bonding. But during ultrasonic welding of the top foil, this wire mesh also gets ultrasonically welded wherever there is contact. And that is anyway good. And you have satisfactory embedment of the wire mesh, which can be readily utilized for your area stiffening. Now, you can produce some honeycomb deck plates for satellite applications, things like that. We have done that. The size of this is something like 350 millimeter by 350 millimeter. And this honeycomb is completely enclosed. You may think that this is just huh? This is fully enclosed. You are only seeing the honeycomb pattern here because that is where you have the wall of the honeycomb and the foil is getting welded to the base. Similarly, you can have internal cooling channels in a very complex manner, which can be completely enclosed. Right? You have serpentine cooling channels here, and after machining these cooling channels, keep building the part to fully enclose these cooling channels. And such parts with complex cooling channels or conformal cooling channels have important applications in many fields of engineering. Then, because there is no significant heating during ultrasonic additive processing, and because you can enclose internal cavities by simply placing foils over the cavity and continue with part fabrication, it is possible to use ultrasonic additive manufacturing for producing parts with embedded electronics, strain gauges sensors, right? There is no significant heating, therefore your electronics won't get damaged during part fabrication. For example, here you see ultrasonic consolidation integrated with, let us say, some direct write technique for depositing the conductive parts. Then you have a demonstration piece here, which is produced with direct write integrated with ultrasonic additive. And here you have a switch. You have a switch here, and if you pull it, your light glows. This is a very simple demonstration of the capability of the process. Because there is no significant heating, you can always contemplate producing parts with embedded electronics, strain gauges sensors, in other words, intelligent parts. Now, this is my last slide. During ultrasonic additive, we have seen that the foil microstructure doesn't really change, right? From our nickel EBSD micrograph. And this capability can be utilized for designing microstructures in a very complex manner. A conceptual, this is just conceptual. We have not done this really. Let us imagine that you have a sheet, from it you cut blanks in different orientations. This sheet has a certain texture and you are cutting it in different orientations. And then you are stacking them together and welding them using ultrasonic approach, right? And then slice new layers from the stack by using different angles, right? And now you have really a very complexly textured layer, and that texture cannot be replicated by any process, right? And using these foils, if you actually do part fabrication, now you have a part which is impossible to reverse engineer, right? And this is the beauty of the technique. You can consider producing parts that are resistant to reverse engineering, and such parts are very useful in defense, nuclear, and other applications because you have to safeguard some secrets with regard to your weapons and other things, right? This is a possibility, and all this is possible because during ultrasonic additive, you are not messing up with the foil microstructure. Whatever is your original foil microstructure, that can be retained. Because you have this capability, one can think of complexly texturing the part the way you want, so that it cannot be reverse engineered. So with this, I close, and I thank all of you for patient hearing. If you have any questions,
What is the maximum size of the component that as of now?
as of now, half a meter. Half a meter in all dimensions.
The thickness.
Yeah, thickness also half a meter, but generally it is not considered for making such parts. You have geometries that are not so tall, but lateral dimensions are something like half a meter. It is possible to use it for half a meter. Of course, your geometry should be stiff enough.
So that was part.
Yes.
In
The,
this
the width is only 100 millimeter with respect to the solar travel direction. Then it can only be built to something like 100 millimeter.
Are the machines assembled and manufactured in India?
There is only one manufacturer in the entire world, that is Fabriconics. This Solidica Incorporation, which originally commercialized ultrasonic edited machines, was later taken over by a company called Fabriconics in the US. They are based in Ohio. This is the only company that commercially sells ultrasonic machines right now. No other manufacturer. And many of the patents are still active, and I don't see anybody really getting into commercial ultrasonic additive in the near future. Yes?
How does the
Yeah?
how does the on how do we machine? How the machine works? Like how we understand
Yeah, we discussed about it. Ultrasonic welding is like your micro friction welding. The sonotrode vibrates at a certain amplitude. Along with it, the top foil also oscillates. So there is relative motion between the substrate and the top foil. And this relative motion helps in the increase of the oxide layers. And plastic deformation ensures intimate contact. And once you have these two conditions fulfilled, metallurgical bonding is accomplished. Yeah, we can actually use foils as thick as 500 micrometer. That is half a millimeter. But typically you use foils of 100 micrometer in thickness or 150 micrometer in thickness. Thicker foils need higher energy input. So that will depend on your sonotrode specification. You need higher normal force. And once you use higher normal force, your ultrasonicator should also be more capable. Otherwise, it cannot vibrate. Right? So, the thicker the foil you want to weld, or the stronger the metal you want to weld, you need higher capability for your machine. Normal force is not a problem. The sonotrode capability is the problem. You cannot achieve any power with ultrasonicators.
In this machine, we capable of transforming other
Powders
run powders into small
it is not possible, not connected with the process. And that is something that you have to consider outside ultrasonic research. Yes, please.
What is the percentage of loss in metal and using?
Percentage of flaws, defects. You mean
90% oxide layer, but we only find micron. across.
అది అప్లోడ్ చేస్తాం.
Reword your question. What is the percentage loss? What is loss? During ultrasound measurement, you cannot measure it. It is only 1 or 2 micrometers. For exceeding strong body, you need to get rid of the oxide layers and achieve direct contact. And removal of oxide layers is accomplished by friction process. And intimate bonding is accomplished by plastic. When two materials are plastically deforming against each other, they issue intimate bonding. And you may ask, what will happen to those removed oxide layer, broken oxide layer pieces? They will actually get distributed in the matrix. And because they are very, very small, just few nanometers in size, you don't really care where they go, because they won't have any measurable effect on the properties. Yeah.
This was only limited to
Yeah, you cannot use this for ceramics, certainly. You can use this for plastics, but you don't have to really have this kind of an exotic approach for plastics, because you have many simpler additive approaches for plastic part making, such as your used deposition modeling or your stereolithography, right? This exotic approach is required to deal with some difficult to fusion process materials. Right? If something can be readily processed with powder bed fusion or some other technique, why do I need ultrasonic editing? Yes, please. Nano components. You mean nanomaterials or nano-sized components? Why you need this to produce nano-sized components? I cannot produce an ant using ultrasonic additive manufacturing. It is actually nonsensically in one thing. Right? You don't have to have a technique like ultrasonic additive to produce a very small thing, right? I mean nanometric or nano-sized part. Yes. I think the next speaker is here. I better start. Thank you all.
I suppose all of you have got educated on ultrasonic additive manufacturing technologies. Thank you so much, sir. Your presence has made a difference here. Because additive manufacturing is something which is known to all of us. But ultrasonic additive manufacturing is one of the most emerging field in the additive manufacturing technology. I would request the permission of the speaker to share a set of slides among the students. Can we have, sir? Can we have the sharing of the slides? A bit selfish, sir, because I am instructing the course of advanced manufacturing technologies for 2 years students.
I don't mind.
Thank you so much. So you all will get
like after.
So we already have set of slides on this presentation soon, shortly. Thank you so much, sir. Thank you very much for raising the attention and accepting our invitation. Please comfortably be seated, sir. Well, as we are a bit delayed in our schedule,
I left my phone there. Water. Yes.
a bit delayed in our schedule. In fact, we have scheduled a tea session from 11 to 11 a.m. But because of the delay in schedule, we will continue the proceedings. Let me introduce the second resource person of the first technical session of second day. He has obtained his bachelor's in metallurgy from IIT Durgapur and master's in PhD from IIC Bangalore. He had been in the industry sector for a few years before he joined IIT Hyderabad. Currently, he is serving as a professor in the Department of Material Science and Metallurgy Engineering at IIT Hyderabad. His research interests include welding metallurgy, phase concentrations, superalloys, and high entropy alloys. Ladies and gentlemen, with this briefest introduction, I request you all to welcome Professor Subhadip Chatterjee, the resource person of this session. Welcome, sir.
Hello. Am I audible? Mic. Thanks.
Welding response of precipitation content, what and became the superalloys.
Thank you. I thank the organizers for giving me the opportunity, and especially to the coming to present some of the things. So, since it is mostly students and undergrad students, probably I will spend some time on the overview of welding of the superalloys, and then present some of our results. Basically, the work of my student Athena, and I have a few collaborators who are doing this work. Professor Chidandaran from IIC Bangalore, Mr. Pavitra from Hyderabad, Professor Pavitra from IIT, and the Ministry of Prevention India. Okay, so let me first find out how many people are not from metallurgy. Okay, few, but most are from metallurgy or materials. And even those of you who are not from metallurgy, I hope you have done some course in metallurgy. If you are from mechanical, so you know about crystal structure and phases, that kind of thing. Okay, so let us move a little bit. And, superalloys. So what are these? So many of you already know. So these are alloys meant for high temperature service. And when you say high temperature, it is expressed as a fraction of its melting temperature. So basically, you have some 0.6 TM of some such number, but they're meant to serve for a long time. So this is the prolonged exposure to high temperature applications in service. That is what makes them super. And you have applications in many sectors, but it starts mostly with these aero engines, jet engines that you have and the associated components, turbine blades, turbine disk, and then you have compressors. So these are combustion, these are some high temperature jet engine parts. And there are some derivatives, aero derivatives, which are basically similar engines for land or marine applications. Then you have some of these are these days especially thermal power plants. People want to increase the efficiency of thermal power plants. The way to go about it is to use higher temperature, higher steam temperature. And today we're talking about 750 degrees Celsius operating temperature for advanced ultra supercritical reactors. These alloys are almost essential to operate at the highest temperatures. Then you have process industries, refineries, where again we need very high temperatures. So these are some applications for the super alloys. And what are the requirements? Okay, when we are talking about high temperatures, typically we talk about its resistance to deformation at high temperature, which we call as creep. So I put the material at a surface level, and it should not deform. First of all, you will use dimensional tolerance, and then it may fail. So creep is the primary thing, but when we are also exposing them to high temperatures, obviously what comes is oxidation. So they will oxidize. So that's a bad thing. You have material loss and problems. Not only that, they are always put in an environment where you have corrosive gases. So hot corrosion becomes another important thing. So these are kind of expected of property from high temperature material that they should resist these kind of things. But what we sometimes do not realize is that along with this, you need some other properties also. They need to be not just have weak state at high temperature, but they must also have a static state. For example, yield strength and enough ductility, toughness, not only at high temperature but also at low temperature, because they will go to some cycles where they will come to room temperature, and this always leads to fatigue. And fatigue can be mechanical fatigue when cycles to the stress, but here it is thermomechanical fatigue. So you have load up and down that introduces thermal stresses in addition to the working stress that you have. So these are very important properties requirement, and almost nothing is like a best. So you always settle for some compromise. So you get somewhat acceptable level of properties. So that is the aim of this level. Now, what are the processing techniques according to which we classify these alloys? And typically, you have this wrought alloys. So, Professor Daniel was talking about coils earlier in the previous lecture. So, these are like basically formed by mechanical deformation. You have rolling 4G extrusion. So, these are the products that you make through this wrought alloys. And typically, they will be used in some turbine applications like a disc. So you may have a forged or a roller, forged roller. And then comes the cast. Cast alloys, you may do some conventional casting, but mostly for this application, industrial casting is the process people use for this alloys. Then you have a special variant of casting technique which is called directionally solidified material. Again, it's a casting process, but with a special property that your grains oriented along a certain axis. That gives better creep properties. And the ultimate level of this directional orientation and indeed elastic of the property in certain parts of the engine is the single crystal plate. So where you remove all the grain elements and they give you a resistance. So these are the different types of processing based classification of these alloys. Now, talking of alloy systems, I will just say about two classes of alloys. Previously, there was also one more. I will just say that. So, nickel base and cobalt base. And since my title of my talk is precipitation strength, I will talk mostly about that kind, those alloys which rely on precipitation strength. Nickel base alloys, why nickel? Question nickel. You may go back to the ultimately each it relies on your diffusivity and activation energy variable of creep. So these two, based on these two, nickel seems to be a good choice because it has very high activation energy and low diffusivity at melting temperature. So these two properties make nickel very ideal candidate for these high temperature materials. Moreover, nickel has one more advantage that it stays in FCC structure from room temperature to high temperature. There is no phase of motion as such from the FCC to another phase. That makes it very attractive. There are certain other alloys which also have this kind of property, but they are very expensive. like cadmium. So more, these are the kind of alloys. But nickel has this problem. So cobalt, compared to this, will come by a close second because cobalt has this transformation. So at room temperature it is acidic, go to a high temperature it becomes acidic. So there is a transformation, but cobalt, the transformation can be suppressed by proper alloy design. So we will see here what we can do there. So traditionally, nickel-based alloys were precipitation statement. So we produce precipitates which will stay stable at high temperatures and deeper strength and other properties. So they are very good strength at high temperature. The downside is that compared to cobalt, they are not so good in oxidation resistance or hot resistance. Now, cobalt situation reverses. They are very good in oxidation resistance, but traditionally they are solid solution statement. You don't have precipitates. Precipitates give the higher strength and high temperature for nickel based alloys. So this is the downside. So the question is, okay, I'll come to that thing. How we can improve cobalt based alloy? First, let us see what nickel based alloys have in them. So the precipitate that happens in the nickel based alloy, we call it gamma plus. The structure is kind of FCC, but it's an ordered structure. So where you know that FCC has atoms at the corners as well as face centers. Nickel based alloys have, in addition to nickel, you have aluminum and titanium, and some 10 other elements. But mostly important is aluminum and titanium in this context. But nickel atoms go to the face-centered position, and aluminum and titanium go to the corners. So what stoichiometry do you have? There is effectively one atom for perimeter for the corners, and 3 atoms for the face center. So you have 3 physical stoichiometry to end up with NiTrAl/Ti in that state. And the structure is called N12. The base is also known as gamma prime. And so this is a, oh, sorry. So I just wanted to have a microstructure. So this is the cubes that are squares in UV that you are seeing are the gamma prime phase. And the dark contours that you see is actually gamma. So it's a strange thing where you expect in most cases precipitates to be the minor volume fraction of the phase. Here it is actually the major one for this microstructure. There are various alloys that these can change, but many of them have this feature that the amount of precipitate is known as the amount of matrix. So when we call it matrix, when you see that matrix should be larger. You call it matrix because of continuity. So you can just go through the matrix continuous form like a maze, but precipitates to go from one precipitate to another, you have to call the matrix. So you have this gamma prime. Now they have been developed over the years. So you have first generation, second generation, third generation, this kind of alloys. And now, in addition to NiTrAl, NiTrAl, so that is NO2, we also have this gamma double prime, which is a BCD base. So that happens in alloy which are niobium, high content of niobium, and when I say high, I mean about 5 to 6%. So when you have niobium of that kind of amount, you form this phase, which we call as gamma, which is a triangular phase. So this also in the triangular phase gives you a very good high temperature strength. Now, these are the phases that we want mostly primarily in the alloy. But we also have something which you cannot avoid, like carbides. You always have some carbon in the trigger, and that forms carbides and carbonitrates. And then you have these phases called topologically closed packed phases. So you have this sigma mu, mostly and various phases, not one level, but they are there. So we have to make do this thing, we can do some alloy design to minimize their bad effects. And one thing that is almost always used in this precipitation statement alloy is multi-stage heat treatment. So one stage is not enough. You go to very high temperature to solutionize everything, then rise to another temperature, get some precipitation, then back to another temperature, basically first you go to temperature, go back again. These are the sort of things that go on. But several cycles are required to get a proper precipitate volume fraction and size fraction, size distribution. That is important. So at different temperatures, this let us say gamma prime, at different temperatures they may give you a different size. And that may be required. As I said in the beginning, you need a combination of properties. So maybe certain size is good for one property, but other size will give you better property. So that's why you have to optimize this and check at every level of each state. If you can check how your properties are coming about. So this is the basically design philosophy of nickel-based supernovas. Now, what about cobalt? I said that they are mostly solid solution initially. Solid solution statement. You put small, you put otherwise nickel in cobalt-based alloy and get solid solution statement. But people have been trying to put precipitates. Why not? Can we not have precipitates in cobalt? Like gamma coil. And can you not have gamma as FCC, as stable phase? Stable gamma coil, that is the stable of our nickel-based alloys. Can you not have such kind of thing? And what should be the equivalent compound for phase for gamma coil in this cobalt-based alloys? So we have to increase to 1 for this structure to come. So people will say CO2 where X can be anything. So people found longer. I think it's like 50 years now. They found that CO3 constant is a good idea. So you can put that. But this work did not get through. And for about 40 years and now in the last decade, it was rediscovered. I think 2006 onwards, 2006 one paper, 2011, and then it took off. So what we now know that this gamma prime usually earlier used to be metastable, meaning the moment you keep at high temperature for long temperature times, this will stay transfer to stable phase, which is no good. We want to stabilize this gamma prime. So what you do, you put a constant and aluminum. That seems to make it stable. What is the downside? You are putting tungsten. So tungsten may be good in some application, but the downside is that it is very heavy. If you are talking about aero engines, you don't want that high density. That is one problem, one issue. Second issue is that handling of tungsten. Since it's a very high melting material, processing becomes a kind of issue. So when you have tungsten. So now, I think 2013-14, around that time, group in the IRC, Hyderabad group started developing these alloys, where you have cobalt aluminum bonding around them. That makes the alloy, the CO3X, the gamma coil was stable, gamma coil phase stable, and you have gamma matrix. The cobalt also is in the FCC state. So you have a good combination, and they did a series of alloy developments, and they come up with this cobalt nickel aluminum moly tantalum titanium, this combination. Okay, there is seen a lot many elements, but if you see the number of elements in nickel superalloy, it's still less. Okay, so you have this aim is to increase the temperature at which gamma can dissolve in the matrix gas. This we call as Solomon temperature. The higher this temperature, the higher that we can put this material at a high temperature surface. So one aim is to increase this Solomon temperature. Another aim is to have a large volume fraction of gamma so that you have strength. So ultimately, this alloy, which I will talk about, gives you a very good Solomon temperature and good volume fraction and excellent high temperature properties. Okay. After this, there have been several developments which I will not talk about, but they have increased it further. So, but today I will focus on this alloy, the welding response. So now coming to welding. So Professor Janaki in previous lecture mentioned about the batteries about welding. But before going to a battery, let us learn what is it. So we have a power source welding through artificial welding, not ultrasonic welding here. So the metal bends and they join, form a metallurgical bond. And it's important to recognize the zones in welding. So when the material bends, this we call as fusion zone. Oops.
That's too simple.
Yeah, thanks. And then the material which is just adjacent to it, we call it heat affected zone because it undergoes some changes because of the heat flow. And one particular layer of heat affected zone, we call it partially molten zone or PMZ, where grains are partially molten. So and then the rest of the material is base material. These are some terminology that is involved. And then what does fusion zone undergo? First, it melts, okay, melting. and then it solidifies as the torch, welding torch only also through welding. So that is the melting and solidification. And then when it solidifies, there is some solute segregation phenomenon that happens. So solid fluid distribution and segregation. And when it finally becomes solid, it undergoes some solid state precipitation or solid state transformation. That is in the fusion zone. In the HSZ, heat affected zone, what happens? For example, you had taken a rolled material, very cold rolled material, not for this alloy, but in general, it will recrystallize. So that is the first thing that will happen. So that is happening in the HSZ. And following recrystallization, you have rainbow and same thing solid state transformation. If you have, for example, in steel, austenite ferrite transformation. So this circuit and values. And since in welding, you can have cycles. Not only a material can undergo this heating and then cooling. If you have multi-pass welding, it will undergo many times. It's like it does in a rigid manufacturing. So you have multi-pass welding. You have this repeated thermal cycles. So this is a basic overview of welding and the terminology. Now, let us come to nickel-based superalloy. So what did I say that I have this gamma I have designed this alloy. Engineer, taker made for just property evaluation. Now what do? I have a welding torch. It melts. The structure is gone. Completely destroyed. So that is the first thing that we can see that welding completely does away with the structure that I made. So what's the thing? So what is going on? So what happens in the fusion zone? Fusion zone, your grain structure is replaced by what we call as dendritic structure. You have this tree-like structure which happens. So the dendrites go from the base metal sides into the center of the zone, center of the fusion zone. So your optimized structure is gone, and then you get this in between the dendrites. You get some of the other phases which often form a nucleic. Okay. Now what is that? I will come in a minute. So you form this structure, and once you are below the Solomon temperature, once the material is below the Solomon temperature for gamma will form. Precipitate out from the gamma matrix. Dendrites are from the gamma matrix. Now gamma will precipitate out. Now there are other phases as I told. For niobium critical metals, you have precipitation of gamma double prime. Just like gamma prime solvers, you have gamma double prime solvers. You know that this will form. Now you have the undesirable phases whereby carbides are not always undesirable. Sometimes they have this at some purpose, but some of the borides are pretty undesirable. Sulfides, then PCP phases, sigma, mu. These are very bad for usually large states. So they will also form. And so one of the disadvantages of fusion processes that unless you take care, you cannot avoid these phases. Okay. So this is what, and then we just show this is the dendritic structure. I don't think you need an explanation. You have this primary arms, this is a columnar dendrite, and then you have secondary. And in between dendrites, you see here the same kind of eutectic-like structure. This eutectic could be between gamma prime or some of the carbides. For example, you have gamma plus MC carbide. MC is a M refers to all the elements like aluminum, titanium. These are M. So they are eutectic gamma and MC eutectic. Then in 718 nickel-based superalloy, you have this lattice phase which forms an eutectic non-liquid. So lattice phase plus gamma forms directly from the liquid. Again, I said the lattice phase is not a good phase, so we have to do something about it. So these are the phases that form during welding or after welding. Now you have destroyed the structure in the fusion zone. And this is showing some more, it's an electron beam weld, so it's a narrow thing and it shows how the dendritic structure looks like. This one would be you see clearly here partially bonded grains from which these dendrites are coming out. So this is just an explanation or more demonstration. Now, this is the other phases. I was talking about MC carbides, you form there, intermediate spaces, lots of other phases. Now, not only other phases, here, this morphology, you see very sharp corners, and these things are in general not very good. So you want to control that thing. And also you don't want a continuous network of these phases. If they form isolated, they may still be controllable. But if they form a continuous network, that is a bad news. Here you see MC turbines in the network, like as well as big particles. So niobium, titanium, knowledge. Oh, about all after learning all about these phases, let us learn about the problems. Because these phases are related to the problems. And to solve this problem methodologically, you have to understand why these things happen. So first problem is solidification pattern. Sometimes it's also called hot cracking. Hot cracking is a bit more general. Solidification cracking happens in the fusion. So what is happening here? You see in the middle, one crack, long crack runs right to the middle, and this is the top view where you can see this. So this happened. You have these red rays, columnar red rays coming from both sides. Okay, and then you have what they are doing as the red rays are going. In your physical methodology class, you learned that solid has similar composition of solute that liquid. So solution is getting emitted to the liquid. It is accumulating in the liquid. So you have a liquid which is very rich in this solutes, and this derives a good. At the same time, you are creating stresses in this material, residual stresses. So as they are forming, they are shrinking. So if they are free to shrink, fine. At this still there is some liquid left, there will not be stresses, but many times they are constrained by the surrounding material. Because this is not a one-dimensional heat transfer, so you have residual stresses. Now residual stresses are there, and then you have a liquid film at the middle, which is very rich in liquid, solid. The melting temperature is very low. So your temperature is dropping, and you have left with this. Now when this liquid is getting solidified, many times you see that as it solidifies it changes, but it doesn't have any more liquid to feed. So feeding of this last liquid channel becomes a very big problem, and you have stresses. So what they will do, they will tear apart the material. So this is the solidification pattern. And typically, this forms with the last stage of solidification. The moment you have a very low melting phase in this system, this product gets irrelevant. Then you have a liquefaction pattern. For superalloy, it is perhaps even more important than solidification pattern. So what is liquefaction? And typically it happens in the heat affected zone. You have grains in the heat affected zone, and then partially molten zone. In the grain boundary, what happens is that sometimes because of segregation, you have water solute content. And this, if you have a low melting phase at the grain boundary, that will melt. That will melt as you are going through the cycle, heat cycle, thermal cycle. That will melt. Now, if it just melts, fine. During cooling, it will also solidify. And now you have a grain boundary between which you have a film of liquid. It can actually solidify without producing cracking, but sometimes it will go through very deep into the grain boundary. Along the grain boundary, this liquid can travel through capillary process. So it's basically surface tension. So in the surface tension of the liquid is very low, so just cover that grain boundary. And if you have a lot of sulfur, phosphorus, this problem gets even more serious. And they will travel to the grain boundary. And again, you have stresses. They will just tear apart. So this is called liquefaction of grain boundaries. This is not a solidification cracking. This is liquefaction of grain boundaries. It is more problem if you have such phases which form at low temperatures. Again, UPT is a usual system. If we have UPT, that means UPT is the lowest melting material. It's a mixture of phases, so we have that melts the lowest. So during heating cycle itself, it will melt. And then it can produce this liquefaction pattern. So this one is showing a liquefaction pattern in the 731, 730 equal 731, 738 well. You see this. You also see eutectic structure here. So basically, it all is related, associated with this eutectic formation. This is there are different laws. What is this about? 738. You see parts of nucleic, and so basically what is this nucleic? So this is a multi-component system, unlike binary system, where nucleic is an invariant reaction. Meaning, it will take place at a single temperature. So you have a liquid and then solution is complete, the below the nucleic temperature. Ideal. This is a multi-component system. So you can go on changing the temperature. This liquid will continue to separate out these two phases. And in this case, gamma and gamma prime, they can form nucleic structures. They are not too equating as in the sense that the degree of freedom is not zero, however, the degree of freedom is not zero. But in still there are two phase mixture that forms from liquid. So you have this gamma prime. This gamma prime is not the precipitate. This is the same phase, but this is forming from the liquid state. This so you should not. So what is the difference between this gamma prime and that gamma prime? The gamma prime that forms during precipitation has a very good interface with the gamma matrix. We call it a covalent interface, meaning the lattices match very perfectly. So as a result, you have very low information available to gamma and gamma prime. Also very low elastic emission. The strain is very less. Whereas this gamma prime is often equivalent. So remaining there is no match with the matrix and this is not very good for strengthening purpose. It will not give you this strengthening. Okay. But the elements that is reaching, it is taking out those elements. So when you go for precipitation, this will be affected. So if you have a lot of gamma prime. But before even you go to precipitation, the syntactic structure. Syntactic structure is a prime candidate for liquidation cracking. And I will show you such things in various experiments. So this liquidation cracking is a big issue in various laws you see, protecting and liquidation cracking. Now, if you could feed this material to the liquid, it is possible to avoid liquidation cracking. You may have liquidation, doesn't mean you will have liquidation cracking. So it is possible to feed the material if the liquid comes and feeds without producing crack. Now, it appears that base metal condition is an important thing. If your base metal has very high hardness, it is also very brittle. So comparatively, relatively. So when you have these stresses, they will produce liquidation crack if you have high hardness of the material. And low hardness, you have less. That is the bar chart shows that you have different hardness and different liquidation cracking. This is related to the carbides. I said that carbides, they are not necessarily a bad thing because if you produce a different kind of carbide, they may give you some grain coverage and resistance. But this one, MC carbide, is typically not that one. So you have AMP-2023, that is a better carbide when it comes to strength. Here you have this cracking, liquidation cracking in 718, which is a niobium strengthened alloy. And I told earlier that niobium strengthened alloy is lattice phase. So you can have lattice phase, possibility of condition of lattice phase here, which forms this gamma plus lattice phase completely. And that is an issue for this alloy. So you have the continuous network of these phases, and sometimes you form liquidation crack in those. Okay, so now what is this showing? Let me just go back one slide back. So this slide, this work actually coming from this, it's a secondary group that 718 plus, which is the development of 718, which is a niobium containing alloy. They observe something that if you increase or decrease heat input in welding, that has an effect. So how do I define heat input? This is linear heat input. How much heat I am putting per unit length of the welding. How do I get mathematically? It's nothing but welding power by welding speed. You will see with the unit of zoom per inch or zoom per minute. So you have different heat inputs. That's how we quantify different welding processes. And you see that when you have high heat input, it's typically considered bad because you have high heat input, material grain growth happens, formal materials. In this way, they found that the liquidation cracking decreases at high heat input. And the reason because you are at high heat input, also makes the temperature gradients in the material less. You have a shallow temperature gradient. Temperature gradient is difference in temperature from one point to another. If you have a lot of heat put into the material, this difference comes down. So you have a shallow effect. And that heat, because this temperature gradient is what is causing your thermal stress, that gets reduced. As a result, liquidation factor, one of the criteria for all these criteria is that two things. You need a stress and you need less susceptible microstructure. So you have a susceptible microstructure here because there is a possibility of new displays, large displays. But the stresses are less at high input. So high input. So they found that by changing the heat input, they could reduce the chance of liquidation cracking. But this is for one alloy, 718. This is not necessarily the true for all alloys. You go to another alloy, 738, and this is not an aluminum containing alloy, this is a normal banana containing alloy. So you see that the cracking is low in the left hand bar. You see that low speed. Now I said heat input is welding power divided by speed. So if you have low speed, that means what heat input is high. And high input seems to give you more cracking. That bar chart is nothing but your total cracking. So this is to calculate the previous level. So this is to tell that there is no one solution that fits all. You have to design based on your alloy what should be a good strategy. Here, for example, you may want to go to low heat input, highest speed. Highest speed is also good because your weld region is actually narrow. So that is a good thing in general on high speed. The third issue that comes here in nickel-based alloys is that I told that you have learned fine. Now you have destroyed the microstructure that you wanted in the first place. So what do? You have to get back the same microstructure. The thing that we have method is that is in our control is heat treatment. To take the material to furnace, put it for certain hours, and then that will get the same kind of structure that we started with before welding. So this is called post-weld heat treatment. Now, it seems that this material, nickel-based alloys, produce cracks. Even if the welding was fine, where you did all the MET methods, no cracking, everything went fine, you are very happy. From that, do the heat treatment, you produce cracks. So, what is happening here? So, you have, I told that residual stresses are already there in the material. And it did not crack at that time. Reason being that when you weld it, you first form gamma. And then during cooling you form this gamma prime. Now some systems gamma prime forms at a slower rate. So if your cooling is very fast, gamma prime cannot form during cooling. So you have a soft material with a lot of stress, but it will not crack. Soft materials good thing that they don't crack. And when you go for heat treatment, goes to heat treatment, now what happens? Gamma prime starts to crack. But before the residual stresses are released to form gamma prime, now you have strong material and residual stresses still remaining. These two interact and they form cracks. Sometimes they call strain age cracking. So you have strain in the material and you do the aging to form cracks. Again, this is an issue for many super nickel-based superalloys, strain age cracking. And okay, so this is a general overview. So you saw in nickel-based specifications, training nickel-based alloys. You have the chance of solute segregation that can produce low energy components, which can lead to either very liquidation or solidification fusion zone cracking. So these are the things, and not only that, you need to do post-weld heat treatment to get back the microstructure that you started with. By doing that, you will get this strain cracking. So these are the issues. Now I will just present two of case studies of this alloys. First, I will present the cobalt-based alloy, which was developed recently, about 8 years back. This alloy, cobalt 30% nickel, 10% aluminum, 5 molecule catalysis aluminum. Again, just to remind you, this is to stabilize the FCC gamma, FCC L1 to gamma prime, this microstructure, gamma prime microstructure. you have a lot of volume fraction of gamma prime with ductile gamma matrix. So that is why we put lots of this aluminum nickel, and basically nickel will raise your nickel and titanium will raise your solvent temperature, and other elements will stabilize the gamma prime. Now, this shows, again, I think I covered this part, the history. But basically, I want to tell that this alloy has a smallest temperature of more than 1050. And you see all other alloys, including the nickel gas alloys, number one or Vespaline. Vespaline is actually a very frequently used alloy. So this smallest temperature is 1030. So this alloy is better than in terms of Solver's temperature. That of course does not tell you the full story, it must have the property. And property wise also is good. Density wise is good because there is no constant, yet you are having gamma open microstructure. So we got this place in the heated condition and got them welded using laser beam welding at ARC Hyderabad. So we did many combinations of parameters. I will show you only one, let's say. So this is a typical keyhole mode laser beam welding. So we get this two penetrating welds in about plates of about 3 mm thick. And this is how the microstructure looks like in the middle. So you have this structure. So what are these small things that you are seeing the corners? They are basically the secondary arms of the dendrites. And in between you see particles. So why do you see particles? Because the matrix has been etched out. What you are seeing is basically the gamma prime. So you have this intermediate phase which is gamma prime, which we found that it is the same gamma prime phase. And then you have in between the diagrams, inside the diagrams, you have gamma prime. So gamma prime phase. So we call this intermediate ID gamma prime, and then specific gamma prime precipitates. Now we know gamma prime, we do electron reflection in transmission electron microscopy. You see, again, even if you go to percent everything, normal gamma should give you the big bright spots, but this weaker spots tell you the identity of the ordering of the space, which probably we tell that it is gamma prime. So, no, this is not NiTriAl, this is CO3. CO3, Al and other elements. That's L12 basically. That is what this ordering is. So this is what NiTriAl. Okay, so we have gamma which has been etched out. We have ID gamma prime, and then we have plain gamma prime which is inside the dendrite arms. Now we also check the composition. So if you do composition analysis across this secondary arms, basically these are columnar dendrites. So you take this direction, you see a periodicity in elements. So basically, what is it telling? That certain elements are more in gamma and certain elements are more in gamma prime. This is called partitioning. So when you are doing the certification, some elements like nickel, they want to go to this gamma phase. While certain other elements like aluminum or moly, they may want to go to the other phase. Titanium is another thing which segregates or partitions very strongly. And certain elements are not so, so they may not have much preference. So now you can also quantify, find out the ratio, partition ratio, and talk about it. Now this is the microstructure that you see away from the fusion zone. So this you take just adjacent to fusion zone, which is this, and then green with the colors are self-explanatory. In the base metal, you have very nice, and you see very high volume fraction of gamma prime. It's more than 70% is gamma prime. Now, as you go more towards the fusion interface here, you see this gamma prime structure is not as distinct and nice cuboids or cuboids like this. So you get, now there are two possibilities that they could melt, and they can give this kind of structure, or they may start dissolving, and what you are seeing is a contrast that is there due to the solute. Different solute are diffusing into the matrix and they are getting this. So there are both the possibilities exist. Based on our analysis, we say that this is like mode of the second. you have this solute fields happening, dissolution and reforming of this gamma. Now we did see few liquidation tracks. It is much less compared to the universe laws that usual laws are broken, but they are there. So for example, we see some backfilling, but certain places, they are definitely there. For this, we need to do statistics, which is not here. This is missing here. I have the statistics, little bit of statistics earlier that I was saying. At certain, this liquidation tracks seem to be near that shoulder. That is very true. And why near shoulder? Because that those regions actually has the changes. You have highest temperature gradient near those regions, and they give rise to this liquidation tracks. We need some thermodynamics. Why? Because we wanted to understand how the solidification is happening. We don't have any phase diagram. So when you have finally a lot of even metallurgical laws, so our people have developed over decades, and we have some kind of phase diagram. But this law we don't have phase diagram because this is relatively new law. So what we can do is that use some thermodynamics software to similar to find out what the phase diagram of this alloy is. And the way phase diagram is plotted here is not like your temperature versus conclusion, because you have high temperature regions. So you have what is plot here really temperature versus phase fraction. So you see that this thermodynamic simulation tells that liquid will start, solidification will start at around slightly below 1400 Celsius, and the fraction of liquid in fall and fraction of solid will increase. So it should give us nice gamma dendrites, no other phase. But what are we seeing there in the microstructure that I gave? We see clear gamma prime formation. So this phase diagram does not tell me what is really happening. That is not very unexpected because phase diagram happens is not what is observed in practice, because phase diagram is not there. In practice, kinetics also is important. Diffusion and other phenomena, those phenomena are important. So this doesn't explain gamma prime formation from the liquid, intermediate gamma prime. But it does explain formation of gamma prime precipitate in solid state. So you see, at around 1100, gamma prime starts to form, and then gamma fraction of gamma falls. To understand what might be happening during solidification, what we do is a non-equilibrium solidification, which we also say as child product solidification, where these are certain assumptions that there is diffusion in solid and perfect diffusion in perfect mixing in liquid, and there is partition. Because of partition, the phase diagram is only valid at the solid liquid interface, not outside. So as a result, you can see that material the liquid will undergo, meaning it will go below its liquid temperature, solid temperature. And you see here, at the end of solidification, we do see gamma prime formation. Now, there is a limitation of this thing. I want to just make you aware that we are using this thermodynamic simulation. It needs some data basis. For this alloys, there is no data basis developed here. You need thermodynamic data, like specific capacity, root temperature. For this alloy, it is not there. What we use was the data from nickel-based alloys. Nickel and copper are similar, so we assume that at least to some extent it will work. And we do see that it does predict gamma prime from liquid, the shine over simulation. But look at the temperature axis, it predicts ridiculously low temperature, which we don't believe is true. Okay. So, but it does show that there is a gamma prime formation from liquid as a you take gamma prime you take it.
This gamma is more stable than liquid, at high temperature, 1400.
So upon 1400 it starts now. That is the liquidus temperature.
But it is showing like 600.
Sorry?
It shows that gamma is in liquid also gamma is there.
No, this starts from the liquidus temperature.
This figures.
So this is the liquidus temperature. Gamma starts forming here. Okay.
So gamma and liquid same temperature is congruent.
No, liquid is zero here. Liquid stops here. At around 1300, there is no liquid left. Everything is gamma, that is 1. So all you have is gamma at 1300. And then you cool the gamma, you start forming gamma prime at 1100, close to 1100. Here also is kind of over prediction because we know that for gamma numbers, this is about 1060. This is not as close to 1100. So there is some mismatch in that prediction. So that notwithstanding that it does predict gamma prime from liquid. So that explanation that why we see gamma prime from liquid can be sort of understood from this. Okay, so next thing we do, properties. And of course, you need full characterization of the wells, welded structures. Meaning you need to do room temperature property study, high temperature property study, 50 degree, all this. But for a quick check, what do we do? And welding equipment, typically the first thing we do is check hardness. That is the easiest. Okay, you check quickest confirmation whether things are fine or not. What you see, and it also tells you how good or how homogeneous the material is. You immediately see that there is a spike in hardness. Base metal hardness was here, around 420 HV. But the heat affected zone has a higher hardness. But fusion zone is soft. That could be a potential problem if you put it in service like this. Because you have a soft material, soft fusion zone, and then you have a very hard zone. Both could be bad, but the soft zone may not take loads, so they may float and they may deform, and this may give you brittle fracture. So this is the hardness maps taken over entire thing. We put a grid and then put in this hardness map. You see that very soft fusion zone, and then in two sides you have hard zones. So this is not good. So we know that we have to do heat treatment. So what we do? We just take this bit.
Some fusion to what makes the microstructure?
So microstructure is gamma plus intermediate gamma prime, and then yeah. So you have this intermediate gamma prime, and then gamma. Okay.
Means literature there is a hardness that in the what is the difference between
So here that's okay. Good thing. So you have this lot of gamma prime which is coming from liquid, which we call intermediate gamma. As I told earlier, this gamma prime does not give strain. This is incoherent gamma prime. Not only that, it is taking away solute from the other means which should have formed gamma prime in the solid state. So this gamma prime is bad. It is not giving any strain, and it is not contributing to the hardness of the material. So we have this drop in hardness in the fusion zone. On the other hand, hardness is increasing in the future HSZ. I will come to that explanation. I have a slide for that. I have time. So now you see what you see. If I just age it after welding, directly, we see that okay, heat affected zone is fine, but fusion zone hardness has now increased more than what base metal is. Now you may think it is a good thing. It may not be such a bad thing, but usually you don't want such variation. You want a material which is sort of uniform in the properties. So if you have non-uniform properties, that again is bad. And from the microstructure also you see the intermediate phase can still be seen. It is not completely gone. We are doing this heat treatment at 800 degrees centigrade. This intermediate gamma prime is not gone. Some of it is dissolved, but not all. And now, if I do a solutionizing treatment before this heat treatment, now I see I have to really draw this weld zone schematic here. My student did it very painstakingly, but it is very difficult to actually locate the weld because things are homogenized after solution and then aging. And you see some fluctuation in the hardness readings, but overall they are the similar starting point. And you see the microstructure is exactly like the starting microstructure. So through heat treatment, you can get back the properties of the original material. And this is the explanation of what going on. So you have different thermal profiles, temperature versus time plots at different locations in the world. This red one is in the fusion zone. So basically it crosses the liquidus temperature. That's why I call it fusion zone. And then the blue one crosses the solvent temperature, which is So this is the heat affected zone. And the green one is base metal, which is heated and cooled, but it does not undergo any major transformation. So what happens in the fusion zone microstructure? So you cause the thing liquidus, and when you're cooling, taking from gamma. Gamma is growing as it is cooling. And this is the temperature difference between the liquidus and solidus. And when temperature at the back lagging end is below the T3, the solvus, you form this gamma prime inside the fusion zone. But you form a large amount of intermediate gamma prime. That is the reason why you are getting very low properties in this fusion zone. Now, what happens in the heat affected zone? You take it up above the solvus temperature, everything dissolves, or at least mostly dissolves, and then you cool it, you form precipitates. But you are cooling at a faster rate than the original heat treatment. What you are getting is a finer precipitates. You are getting the same gamma prime, but the size is higher. And in metallurgy, smaller is stronger. Use the load, use the time. So you get a higher hardness because of this fine precipitate that you get from cooling. Okay. So this is basically the summary that we get. We could weld this new material which shows very promising properties. But welding is a document because without welding you cannot put in those service applications. Okay. So now it welds well. We have some issue with equation tracking, that's normally helping. Over here, proper design of the welding parameters because we saw they happen at the locations of the highest stress. And then you have gamma prime, intermediate gamma prime, which is reducing the strength, but we can get back the strength by reducing. So that is the summary. Okay. How much strength? Over? Okay, then I will stop here. Okay, fine. Then I will stop here. Thank you for your attention.
It was always was a low temperature application. But here there's almost like
Yes. Right.
So
that initial cobalt-based alloys was solid solution strength. So their strength are lower. So they are typically for lower temperature applications. Below 700. Now this solvent temperature is very high. You can go. Common people have to test the high temperature properties and take it results. But it can easily go over 800. So that is the advantage.
actually, where can we see this always from the
So this is what, so for example, these are not made applications, but these are for this application. When you go to this combine this at 800, centigrade, you can put them in the jet engines or even in land-based engines, land-based steam turbines, for example, marine turbines, combustion, the lower temperature section, not the high temperature section, compressors. This stability was tested. They found within their, I don't remember the exact number of hours, but it is stable. Okay. They tested without load though. So for high temperature thing, they have now come up with a better alloys with some chromium addition. This seems to give even better properties than that. But they have tested. Also, they have tested the hot deformable thing. So the Panikumar was working on that. How do you produce these parts of this material using hot deformation? They produce the deformation maps. So this seems to be promising in all aspects. Welding is a key thing that processing-wise, fabrication-wise, welding is very important. So this shows that this is weldable, provided you take care of certain precautions and do some treatments afterwards.
You said DMF after weldability.
Yes, TMF is a very important thing.
Because it is a laser welded.
Right.
Because that produces a very thin dimensions of the
Right.
How you are able to differentiate the HZ and fusion zone when we go to the microstructural?
That's a wonderful question. It's actually very difficult. Because we struggled a lot. It seems the best way to differentiate is through hardness. So you see a very clear differentiation. And you can also sort of say from the microstructure qualitatively that your base metal gamma prime structure is very different from your heat affected zone gamma prime. You have seen that most microstructure contrast. From there you can sort of say, okay, this is changing, this is heat affected.
Right. When analysis, like
Ah.
they have shown some TM
Ah.
things also.
Right.
So in that one, what we HMP, we can find some kind of it.
Right.
But when we go for the TM or PST particular,
Ah.
so if we have to focus on the particular role, it is becoming more difficult.
So there is a few solutions. These days you can make local samples of TEO in an instrument called FIU. So you go to that particular location, you know this is my heat emitter zone, take out the sample from there. That is one way. Another way is to reverse engineer. So you suppose you measure the temperature in different zones as a function of time. Now you can take the temperature profile, make a bulk specimen, let it undergo the same cycle in a thermomechanical simulation, global. So then analyze, because then it is easy. So these are the two primary approaches that I am aware of people can do.
One percent students. 1% students. I suppose there are no questions.
Lunch is there.
What if you weld nickel into one?
Sorry?
What if you weld these two separate?
Yeah, that is interesting. Yeah. We will see a gradient. I could not actually present the nickel. Yes, that's a thing, but typically they are interesting for me because what is happening at the microstructure level. But typically, industry-wise, they make more of that. So, uh, mhm. Yes. Right. Functionally graded. Yeah, that would be nice instrument to do that. One of my students actually bring two different nickel-based alloys. I think one was Russian grade and another was US grade. So they wanted to do this identical actually one on one. That is an interesting thing.
Thank you so much, Mr. Sapradi.
Thank you very much.
Now,
Because this is whatever I present is published, so I can issue. Other project is still the process, so I will share the same. I just same with the
so at this point, we should break for lunch. No matter how much time is given, please. At 1:30, we should resume. At 1:30, we all should resume back. Right? Is it clear? Fine. Thank you so much.
Yes, I cannot unfortunately.
So we can go on.
Next year, the faculty
Yes.
Good. We are going to ask them.
But unfortunately, we need to place it in the amendments.
Oh, you're not looking for this section?
I have put
No, I am in-
Oh, you are leaving.
No, not leaving, I have invitation.
No problem. Like any day you can call. We are at the not far. Here no problem. Doing something different. Absolutely.
ఈ లైవ్ రన్ అయితేనే ఉంటుందా?
ఇలా మైనస్ వచ్చి ఎక్స్పైరీ కదా దేవుడు క్యాల్కులేషన్ చేస్తారు ఐవల్ పెట్టుకుని ఒక 8 ఎక్స్పైరీలు వస్తాయి కదా నెలలో 8 టైమ్స్ 5000 డబుల్ అయితే ఏమవుతుంది 5 into 2 power 8 కదా 2 power 5 ఏమో 32 64 128 128 253 512 512 into 5000 ఆ మాత్రం పెరిగిపోతుంది మరి ఇంకా మన దిగుడులో అకౌంట్ ఓపెన్ చేయాలంటే 4 లక్షల డాక్యుమెంట్లు అడుగుతున్నాడు శాలరీ స్లిప్ ఇన్కమ్ బ్యాంక్ స్టేటస్ మళ్ళీ ప్రీవియస్ డిమెట్ అకౌంట్ స్టేట్మెంట్ ఇన్కమ్ గురించి దాంట్లో ఆప్షన్ అది బ్యాంక్ స్టేట్మెంట్ ఓకే ఆప్షన్స్ అంటే అందులో ఆప్షన్స్ రిజిస్టర్ చేయలేదు డిమాండ్ అకౌంట్ ఓపెన్ చేసినట్టు కదా నాకు ఏమైందంటే ట్రేడింగ్ బిలో చేస్తే వాడు నెలకి 2000 అంటున్నాడు చార్ట్ కోసం ఆ స్టాటిస్టికల్ చార్ట్ లో పిరియోడాలు క్వాంటిటీ వచ్చేస్తుంది ఆ రేటింగ్ ఈ అమ్మాయి ఎంత
Last time
అది బాగుంటుంది